The examples that we've looked at so far have all had x times some transcendental function, and most often we used x as the parameter for u. We haven't tried any examples where we used x squared or x cubed or any other value of n as an exponent other than 1. And what happens is you actually end up in a situation which requires you to repeat the process of integration by parts many times over. So, for instance, let's take a look at the simplest of those examples, which would just be the integral of x squared times sine of x. All right, so if we are integrating this, we would start by identifying what we would like to use for u and for dv. So using ILATE, the algebraic part comes before the trigonometric, so we would use x squared for u, and then sine x for dv. The derivative of x squared would be 2x dx, and the integral of sine is going to be negative cosine. Okay, now if we apply integration by parts, then what happens is our formula, of course, says take u times v, so this would be negative x squared cosine of x minus the integral of v du. So v being negative cosine of x and du 2x dx. Okay, simplifying here, we can see that this 2 can come out front of the integral and we can make a positive. So let me go ahead and do that next. So I'll just write this as negative x squared cosine of x plus 2 integral of x cosine of x dx. Now, what we wanted to occur did happen. So for instance, what we wanted is for this integral to be simpler than the original integral. And it certainly is. It is simpler by a degree of 1. We went from x squared down to x. But in order to integrate this, we still need to do another iteration of integration by parts. So for instance, for just this part, I would define u and dv again. So u would be x and dv would be cosine x dx. So that du is dx and v cosine, its integral is going to be sine. And now what we end up with is negative x squared cosine of x plus 2, and then I'm going to write out the rest of this using the integration by parts formula. So that would be u times v, so x sine x minus the integral of v du, which would be the integral of sine x dx in this case. And we still have another integral to go, but luckily this one is just the integral of sine, which is one of our basic integral formulas that we know how to do already and doesn't require the use of parts integration. So it looks like I would have plus 2 times the quantity x sine x minus the integral of sine is going to be negative cosine, so that's going to make this plus cosine x. And then I would have a plus c. And if I want to finish the problem off, it's not really necessary, but I think I'll go ahead and distribute this 2 in. So this would be 2x sine x plus 2 cosine x plus c. Now, I think you can see the problem here. if we were to have x cubed or x to the fourth or any other power of x, we would have to do that many rounds of integration by parts. So luckily, someone came along and discovered a method of simplifying this. And that's what's known as the table method. So you wouldn't necessarily use the table method for integration by parts if you only had x times sine x, for instance, but you could. It would just be a little bit overkill. But absolutely you would use it for any other power where n is greater than 1. So here's how it would work. So we start off listing out values of positive and negative. Okay, I'm going to make a table of those, and I'll write them in just a moment. And then we're going to write out functions u, and then we're going to write out functions dv. All right, the reason, of course, for the u and dv is the integration by parts process. That should be obvious, I think. The reason for the positive and negative, what happens is this negative in front of the next integral n line changes the sign of what comes inside. And that happens at every single step. It flip-flops at every single step of the process. So it's important to have in this table method. So what I do is u is generally going to be decided upon by the algebraic part. So in this case, the function x squared. And then what we do with u is we repeatedly differentiate it. So as you can see back here, and I apologize for all the scrolling here, but we go from u, which is x squared, to du, which is 2x dx. And then we have something similar to that. It's just x, okay, that's fine. But we take its derivative. And we kind of have this, repeated differentiations. We're going to do that until we get down to basically 0. So this would be 2x, then 2, and finally 0. So it's important that we have an algebraic piece here for the table method so that this will end. Like if I had e to the x times sine x, this wouldn't work because e to the x is never going to result in a derivative of 0. All right, then dv. dv here is the function sine x. And of course, normally we would write sine x dx, but we're really just concerned with the function itself. But now I'm going to start listing out the same number of integrals of sine. So I'm integrating this list, I differentiated this list. So the integral of sine x is negative cosine x. The integral of cosine is just sine, but since this is already negative, we'll leave it. Sine flips to cosine, but it also changes the negative to positive, so this is going to be cosine x. Okay, and lastly, the positive and negative, easiest column yet. You just start with positive, and then you just write negative, positive, negative as many times as you need until you get to the last one. Okay, now this has set up a chain of items, and we don't actually use this in the process anywhere. So if you go back up to what we did up here, the sign never gets used in the next steps. It's always v instead of dv. So that's not going to get used, nor is these two items here. All right, but what is going to be used is this. The product of these two items along with this one diagonal. And then the product of these two items along with this one diagonal, and these two items with this one diagonal. All right, so we end up with, we've got a positive x squared and then a negative cosine x. So that's going to be negative x squared cosine of x. Then I have a negative and a negative. That's going to result in a positive. Then I have 2x and a sine x. And then this one's all positive, and then I have 2 cosine x. And finally, a plus c. And if we scroll up enough, can we see it? That's good. We have the exact same answer. And you've got to admit, this was much better to go through. So just as a recap, so that you have them for later, here are the steps of this process. 1. Pick u and dv. Same first step as if you're doing integration by parts, as you would normally. 2. Differentiate u until you get to 0. So it's important this is an algebraic style function so that this would actually happen. 3. Integrate dv an equal number of times. 4. Add an alternating sign column, starting with positive and then flip-flopping positive, negative, positive, the same number of times as your other rows. And 5. Multiply the columns using the pattern shown to the left in order to get your integral. Let's see one more example of that. All right, so here I have the integral of x squared divided by e to the 2x dx. So first thing is I'm going to rewrite this so that it looks like a product, because we generally think of integration by parts working whenever we have a product of functions. Right? And I could have chose to use x cubed, but just for, if you can do x squared, you can do x cubed or higher. So I'm just going to leave it as an x squared example here. So we have a column for signs that are changing, a column for the function u, and a column for the function dv. Now, u is my algebraic function in this case, and it would differentiate as 2x, then 2, and finally 0, which means I would need positive, negative, for these signs. dv is the function e to the negative 2x. Now, e to the negative 2x needs to get integrated. And anytime you have, say, like e to the x, or just sine x, you definitely need to know how to integrate those. Those are just basic integration formulas. But if you have something more complex, like for instance e to the negative 2x, the integral is still basically itself, but it's only off by a multiplied constant. And it's definitely in your best interest in this course to learn how those multiplied constant works. So if it's just e to the negative 2x, instead of going through the steps of u substitution, just know that you're going to multiply by a half, or if you want to think of it as divide by 2. You can prove it through u substitution, but this is where you're going to want to get to be able to just look at this and know that the integral would be the original function divided by the constant. So that the next one in the list would be positive 1/4 e to the negative 2x, and then negative 1/8 e to the negative 2x. So that our integral, of course we skip over this one, we don't use it, we don't use these. We go from here down this way and so forth to get these remaining terms. So looks like I would have negative x squared over 2 times e to the negative 2x. The next term is going to be negative. 2 over 4 would be 1/2, so this would be x over 2 e to the negative 2x. And the last term will also be negative. 2 over 8 would leave me 1/4, so just 1/4, and then e to the negative 2x plus c. And then just double check to make sure everything works out the way it's expected. That right there is your integral.